what do we have in here? We have hydrochloric acid. Obviously the Cl minuses are the big ones. You can draw this on the side. You have, we're not going to draw this, but just on the side so you know, these are ions in solution. And you have the water. You have to draw at least 3 waters to get a hydrated shell. And what is the name of that bond?
Are we drawing this on the back?
On the side.
In the square.
On the side. Ion dipole. This is a hydrated shell.
Which one?
Wait, like here?
Yeah, on the side.
Where?
In the square.
Right there.
In the square?
Outside the square.
No, but just like
On the
here.
side.
Hydrated shell, if you were to have another water, then you will have hydrogen bond. No, you love bonds.
You heard that? You
Yes.
really did hear it.
Dipole, dipole.
I didn't hear that.
It's a dipole, dipole, but it's also a hydrogen bond. Now, when you have the H plus that he's calling H plus, it's truly not H plus. It's H3O plus.
Is that?
Those are the little red things.
Yeah.
Those are H3O pluses. And how do they bond with water? So these will bond to the oxygen side of the water.
Wait, what is that?
H3O plus. And this will be the hydrogen side of the water. And it all has, is that hydrogen bonding too?
Yes. Between, yeah.
Because it's in between 2 O's, right? So that's all hydrogen bonding. We don't necessarily call those hydrated shells, although they look like a hydrated shells. Normally when we're talking about hydrated shells, it's those ions. This is also an ion dipole and hydrogen bonding. Because the H3O plus is an ion. Now, that is the stuff we know. I'm just refreshing our memories. That's all interbonds. Intrabonds will be the polar covalent bonds within the water. Now, we're going to do a titration, which next class, we're also going to do it online, and then we'll do it real life.
What are those blue dots?
The blue dots are the OH minus, is sodium hydroxide. This is the OH minus. And the Na plus is the little tiny, the little ones, because they lost electrons. On this side, we're going to have how much water, how much sodium hydroxide is dropped. 10 milliliters, 30 milliliters. 60 milliliters, 80 milliliters. How much of that we are dropping? And on this side, we're going to measure the pH. So it'll be like 1,714. We said that this acid was 0.1 molar, and we have 60 milliliters of it. Of the acid is HCl.
Why is so thin?
She's so happy. Okay, you see that?
Have a good day.
You see, you're so happy.
Serving our country. I'm serving my community. You can't be bad.
I'm gonna complain.
I'm Wisconsin. Go for it.
Yeah,
You already
very
gone.
good. I have the class. So we're gonna have sodium hydroxide, and the volume is whatever we drop. This in a humongous bidet, so we have an unlimited volume. And the molarity is also, I'm pretty sure it's also 0.1.
Miss Thompson, is the chart that you're drawing already?
Yes, it's already drawn for you. So the first thing that we're gonna do is, what is the pH? Before, we're gonna have a pH meter here. Something that is gonna measure the pH. What will be the pH before we drop any sodium hydroxide? So there is a valve here. That valve is closed. What is the pH before we drop any sodium hydroxide? Where were we? I guess you. What is the pH?
It's below 7.
The molarity is 0.1. So you can write it in a different way. It's 1 times 10 to the negative 1 moles per liter, right?
Wait, where did the 0.1 come from?
I told you that both these solutions are 0.1 molar.
Oh, and so that's what the pH is?
So that is the concentration. The molarity is the concentration of hydrogen ions or hydronium ions in solution. That's the concentration of H plus or H3O plus. It's 1 times 10 to the negative 1 moles per liter. Right? That's what this 0.1 molar is telling me is I have that concentration in that particular solution. So I have 1 times 10 to the negative 1. How do I find the pH? What is the formula for pH? Harrison?
Oh, I didn't.
What is it?
Negative log.
So the pH, negative log of the hydrogen or hydronium concentration, right? What is the negative log of 1 times 10 to the negative 1, Harrison, your math wizard?
I don't know. Is it 1 pH?
1. What is the pH? What is the negative log of 1 times 10 to the negative 2? Kate, what is the pH of 1 times 10 to the negative 5?
Point 000. How is that wrong?
So the pH of 1 times 10, she was out. 1 times 10 to the negative 1, the pH is 1.
Okay, yeah, no, sorry.
1 times 10 to the negative 2 is 2. 1 times 10 to the negative 5.0005.
It is fine.
I'm kidding. We all get distracted. We all get distracted, but it happens. So it's 5. Now, 1 times 10 to the negative 8, what is the pH? Woman.
0.
No! 1 times 10
It's
to...
8. It's 8.
So 1 times 10 to the negative 1, what is it?
1.
1 times 10 to the negative 2.
2.
1 times 10 to the negative 8.
8.
Yes.
You have like negative pH.
You supposedly, this is what we use, 0 to 14, but it could be way higher and it could be way lower.
So like 12 molar H2SO4.
Now, the pH of this one, before we put anything in there, is 1, right? That's what we said. 1 times 10 to the negative 1 was 1. So that's your point A. What do you have? Just your strong acid. And what does that measure? The concentration. So the negative log is, the stronger the concentration, the lower the pH, right? Now, if you are going to, whenever you reach the equivalence point, where are you when you reach, do you remember? Oh, did we talk about the equivalence point before?
No.
The equivalence point is when you neutralize all of your H's, you make them water. You drop OHs and you neutralize them all, right? So the equivalence point happens when? 60 milliliters, right? That is your equivalence point.
But what if the molarities are different? How do you calculate for it?
If the molarities are different, then you have to figure it out. Most of the time the molarities are different actually, right? So you have to, when you neutralize all of them, like if it was 0.2, right? 0.2 molar, how many would you require to reach to the equivalence point? Just you have to just drop 30 milliliters and you will have canceled them all out, right? Because you have twice the amount of that.
Oh, so you need half of it, so it'd be 30 milliliters?
Yeah, if the molarity were different, right?
Is there an
Well, the
equation?
equivalence point is always whenever, yes, there is an equation to figure out the equivalence point, which we have talked about it somewhat. It's called the boom boom equation.
Oh, yeah.
Molarity times volume of the acid is equal molarity times volume of the base. Why? Because molarity times volume is the number of moles. When the number of moles are equal, then that means that you cancel them all out, right? And in reality, this equation should have a 1 over n, which is the coefficient of the acid. That takes care of your crossing the bridge, and this is the coefficient of the base. What do I mean by that? If I have an acid that is HAC and a base that is H2A, I need to do it with a real acid, H2SO4 plus NaOH, that will give you what? H2O plus NaSO4, right? And when you balance it, what do you have to do? Right? So when you are doing the boom boom, it will be 1 over 1. So you don't really write that one, but this will have been 1 over 2. That's what I mean by 1 divided by the coefficient. You do not have to use boom boom. You can use stoichiometry, but this is just simpler.
So you have to have the 1 over n though?
Yes, because otherwise you won't have the 2 to 1 mole ratio, which is the crossing the bridge. So you have to have it. 99% of the time when we do these things, we will not use a diprotic acid or something that requires a coefficient, but just in case you ever have it. So most of the time will be like HCl and NaOH, so it doesn't matter because they're both a 1-to-1 ratio, right? Like 99% of the cases for us right now, but eventually you may get one in which is not a 1-to-1 ratio, and you will need those in order to get the exact same thing. Now, the equivalence point is when you neutralize the whole thing. So we said that is reached when you drop 60 milliliters. So what happens when you add in half the equivalence point? Half the equivalence point will be when you drop 30 milliliters, right? If we have 6 total H's, how many do you need to cancel? For half equivalence? 3, right? So when we drop 3 of these ones, what happens, these ones become water, so they disappear, right? An OH and an H will make water, right? Everybody okay with that? If I drop the OH with the H, it will become water. That's what we call neutralization. This one will disappear, so in the second case, you won't have these ones. Does anything happen to the CLs? Spectator, I say stay there. What am I missing in this picture? May? I drop NaOHs, so what am I missing? For the, what? The NAs, so I'll have to have 3 NAs over here somewhere that were dropped, and they're also a spectator. So the CLs are the conjugate bases of a strong acid. They don't do anything. And the NAs are the conjugate acids of a strong base. They don't do anything, both negligible, right? So you have those 3 NAs, that should be how your second sketch looks like. The one over here, right, for B? It said not to draw the waters, so you don't draw those. No, not to draw the waters. But to draw everything else. What happens at this point? So you drop 30 milliliters of a 0.1 molar solution. Right? And you originally had 60 milliliters of a 0.1 molar solution. Ooh, I don't know if I need to do this or not. I'm going to introduce a little concept. If you like it, great. If you don't, we'll go back to not using this, right? Just in case, I kind of love doing this. I love multiplying 30 milliliters by 0.1. I call this millimole per liter. Millimole per milliliter is the same ratio, right? So 30 times 0.1 is what? Yep. That's 3 millimoles. If this gets confusing, I'll bring it back. We'll divide it, make it liters and ta-da-da. But I kind of love using it because then you don't have to deal with the little tiny numbers and you don't have to convert as much. 60 milliliters times 0.1 will be what?
6 millimoles.
6 millimoles, right?
Millimoles?
Forget this for now, and if you don't like it, and I'll go back and teach it with moles. But
Okay.
this may make your math. I'm just gonna do it. If you don't like it, we'll go back. You have 6 millimoles here. You drop 3 millimoles. How many millimoles do you have left? Of the acid, right? So you end up with 3 millimoles. You subtract those two, and you end up with that you have a leftover of 3 millimoles of HCl, right? To find the concentration, you drop 30 milliliters, right? To find the total concentration. Now in here, the level went up a little, right? Because I dropped 30 milliliters. Does that make sense? I had 60 and I dropped 30. So how can I find my new concentration of HCl? My new molarity. What is the formula for molarity?
Moles per liter.
Moles divided by liters, or millimoles by milliliter, right? So what do to find my new concentration, I'm gonna divide it by what?
30 milliliters.
3,000.
You had 60 milliliters, and
90.
you added 30 more.
90 milliliters.
So you are left with 3 millimoles in 90 milliliters. See how beautiful that is? You don't have to convert all that nonsense. 3 divided by 90 is what? I don't know how. Some people may be able to put this on their heads. Not me.
30.
What?
1/30. 1/30.
Yeah, well, what's that number? We need the number. We're all lazy.
0.03
Really? 0.033 repeating. I always like to carry more than I need. Can I say that So milli and milli can cancel, so that's the same thing as that in moles per liter, right? It's a ratio. So if you like this, we'll do it. If not, you change this to liters and then you do the
What
normal
did you
stuff.
just find?
What am I finding?
Yeah.
So now I have the concentration, right, of HCl. How can I find the pH right here?
Oh, so adding a base lowers the concentration?
Adding a base neutralizes some of the acid, so it lowers the concentration of the acid. So if I had 6 H's in here, when I added 3 OH's, it made them water. They went away. So now I'm gonna have 3, but I also added water, right? I cannot neglect that water. Because now you have a greater volume, so you need to account for that. I have a feeling we're not gonna do weak. We're just gonna leave it at strong. But 3 divided by 90 is moles per liter, right? How do I find the pH of that at this point? This is the concentration. Negative log. So what is the pH of that? The only one that is got, oh, you have a calculator too.
1.4 something.
So it's 1.4. It's a little higher, right? It became a little bit more basic. Why? Because we are neutralizing the acid, right? Everybody okay with this?
Can we just use the graph?
What?
Well, when we do this, many times you will have to make the graph, right? Like this time the graph was made for you. And you still need to, the most important thing here actually is understanding what you have. So what do you have at this point? At this point, you're gonna have, who cares about the spectator ions? Try to not see them. At this point, what you're gonna have is just acid in solution, less than what you started with, right? Understanding that is important.
So like a V box, we just need 3 like acid things.
Yes. Normally, I don't even draw the spectator ions. Here, you're gonna have 6, 1, 2, 3, 4, 5, 6, right? When you're here, you're gonna have 1, 2, 3, probably a bigger solution, right? And when you're here, how many acids do you have? None. So what is the pH here if there is no acid? 7. That is the equivalence point. That's when you neutralize the whole thing and you have a pH of 7. Right? The acid is the H+. If we neutralize it all, we just end up with a whole bunch of water. And basically we end up with all the spectator ions, which mean nothing. Right? The NAs and the CLs, the sodium chloride. What would happen if you evaporated that water? Where were we? Darren, what happens if I have this water and I evaporate it? I just let it be an evaporator to boil it. What would I get? Sodium chloride. Could you eat it? Yeah, you could. Sodium chloride, that's what you get, right? They go back together and you have sodium chloride. You neutralize the whole thing, it's just water. That's what neutralization means, you're getting water. Now, let's see how much we actually understood. Now I'm going to add 80 milliliters. So I'm going to add another, well, we were in 60 here. I'm going to add 80 milliliters of the base. So what do I have of the acid? We started with 60 milliliters. Oh, by the way, did you like the millimole nonsense or do you want me to go back to changing it?
Just done.
What?
No millimoles.
No millimole? I know
Wait,
millimole.
so
don't like
for the third drawing, it's 6 chlorine and 6 sodium.
For the third, you have 6 chlorine and 6 sodium because all the other ones became water. You didn't like millimoles?
No, I thought it was easier.
Right?
If I
It's
like,
so much easier.
like,
No
can
conversions.
then you don't have to convert like the
At
60
all.
milliliters.
you
and-
do
Nothing.
the other one the other way?
So let's do this one the other way.
6 chlorine.
So instead of 60 milliliters, I need to write it as what?
Point 0.06.
0.06 liters, and then the concentration will still be 0.1 moles per liter, right? And for the base, I'm gonna write the volume as 80 milliliters, so it's 0.08 liters, 0.1 mole per liter. What is the total here? 0.06 times 0.1. You see these numbers? I hate them. They just look weird and ugly. Moles of HCl. How many moles have I dropped? 0. I guess it's not that bad.
0.008.
Moles of NaOH. You subtract them, right? Because they're gonna cancel whatever cancels, and you end up with what?
0.002.
Moles of NaOH. Right? That's not a concentration. So I need to get the concentration in order to get anywhere. So that's moles. How many milliliters do I divide it by, or liters, sorry. How many liters do I divide it by?
0.14.
So it's 80 plus 60, right? Which is 140, right? 0.14 liters, but you have to keep converting. What did you get for the concentration? What? 0.0142 moles per liter of NaOH. Extra, that's why you had extra now, so now we're gonna be over here somewhere. If I do the negative log of that, what am I getting? Marshall,
The negative log of what?
the negative log of this concentration, what am I getting?
1.
The pH or the POH?
pH. OH.
POH, you need to pay attention to that. Because we are measuring pH, but this is the P. Now, why POH? Because we cancel all the H's, right? So now we only have OH's, right? What do you draw in your drawing? Oh, I took everything out. But what you had to have is you had to add just basically 3 OH's. No, not 3, 2, right? 2 extras, and then all your spectator ions in there. All your spectator ions, but you had those 2 extras, which is all that we care about. No more, now we have OH concentration. The volume we said was 140 milliliters. So, in order to get the pH, what do we do?
You find the pOH and then subtract 14.
14 minus the pOH. And the pOH is the negative log of that. 14 minus that should give you a high number. That should be your D. And if you want to just draw the 2 OHs, although you do know that you have a lot more of your stuff.
12.15.
12, so does it agree? Yeah? That should be your point D at 80 milliliters. So you use millimoles if you want, you use moles per liter if you want. Just realize that concentration can be in millimoles per milliliter or it can be in moles per liter. what happens if you happen to have to use a molar mass in order to change anything? Can you say that if the molar mass is, let's say, 2 grams per mole, would that be the same as saying 2 milligrams per millimole? It's a ratio, right? Doesn't matter. Anything that is a ratio, you could say grams per mole or milligrams per millimole or kilogram per kilomole, right? It's no big deal. So if you think that the math is easier and it makes more sense to you, then use millimoles and you're fine. Realizing that anytime you have a ratio, you can just choose to have milligrams per millimole or milliliter per millimole or to have that. I think we're saturated. So how much time do we have?
4 minutes.
Oh, okay, so it's a good time to